Hello everyone. Today I have taken a question from eigenvalues and eigenvectors. As you can see here, if A is a matrix of order 3 cross 3 which is given as 1 0 0, 1 0 1 and 0 1 0, and we have to show the result a to the power n equal to a to the power n minus 2 plus a square minus I, and which holds for all integers n greater equal to 3. So basically this question is a combination of eigenvalues and eigenvectors, as well as here we have to use the concept of principles of mathematical induction. So let's just start solving the question. First we are supposed to find out the characteristic equation. So let's just find out the characteristic equation. So the characteristic equation is determinant of a minus lambda I is equal to 0. So let's just find out a minus lambda I. First we are finding with respect to the matrix 1 0 0, 1 0 1 and 0 1 0. This is the matrix A which is given in the question, minus lambda into an identity matrix which is 1 0 0, 0 1 0, 0 0 1. So let's just find out the result. The result will be 1 minus lambda 0 0 1 minus of lambda 1 0 1 and minus of lambda. So here we have a minus lambda I as this matrix. Next, as per this characteristic equation, we have to find out the determinant value of this matrix. So let's just find out a minus lambda I, determinant of it. So as you can see, with respect to the first row, we are supposed to expand it, but there are two elements which are both are 0. So we can ignore this part. So 1 minus lambda into minus lambda 1 1 minus of lambda. So we are getting 1 minus lambda into lambda square minus 1, and its value which I already have mentioned there, the characteristic equation, determinant of a minus lambda I as 0. So that's what I have substituted here. The next part is we need to multiply this expression. So let's just multiply the same, lambda square minus 1 minus lambda cube and plus lambda. So basically what are we getting from this step is lambda cube equals to lambda plus lambda square minus of 1. So you see, here I have shifted this lambda cube in the left hand side, and so the rest of the expression will be same as before, like lambda, lambda square and minus 1. So here this step can also be expressed in this form, 3 minus 2 plus lambda square minus of I. But why are we expressing it in this way? The fact is, see, here we are supposed to show a to the power n equal to a to the power n minus 2 plus a square minus I, this thing. Now we have to follow the characteristic, rather the Cayley-Hamilton theorem, because from here we can deduce the rest part of this question. So as per Cayley-Hamilton theorem, I'll just write the statement of this Cayley-Hamilton theorem. every square matrix satisfies its own characteristic equation. So see, the characteristic equation of the matrix A is basically this equation. Now this equation will be satisfied by the matrix A as per the theorem, as per the statement of this theorem. So I repeat the same thing once again. This is the characteristic equation of the matrix A. So this equation will be satisfied by the given matrix. So what we can write is A cube equals to A to the power 3 minus 2 plus A square minus I. So the expression which was given in the question, it is verified for n equal to 3. That means the lowest integral value of n. Next, we can assume that this particular statement or this particular expression is also true for n equal to m. That means we are taking an arbitrary number m here. So let the expression be true for n equal to m. So what we can write is a to the power m equal to a to the power m minus 2 plus a square minus I. The next part, rather the last part of this question is, we have to show the result is also true for n equal to m plus 1. Because usually what we do in case of principle of mathematical induction, we check an expression for a specific value of n, like 1 or 2. Then what we consider is the statement be true for n equal to m. And the last part is we also check whether the expression is true for n equal to m plus 1 or not. That exactly we are going to do right here. So a to the power m, let's check whether we can write in the specified format or not. So a to the power m is equal to a to the power m into a. We can express it. We have the value of a to the power m here, that I am going to substitute a square minus I into a. So after the multiplication, this would be a to the power m minus 1 plus a cube minus of a. See here, we also have the value of a cube. So let's just substitute the same. Earlier we have obtained the value of a cube as a plus a square minus of I, that I have substituted here. We also had minus of a in the previous step. So we can finally cancel out this plus a and minus a, and so this expression will be hence, sorry, I made a mistake in the previous step. A to the power m minus 1 plus a square minus of I. So finally we can write it like a to the power m plus 1 minus 2 plus a square minus of I. So see, the statement is verified for n equal to m plus 1. So that I am going to write here. Therefore, the expression is true for n equal to m plus 1. It follows a to the power n equal to a to the power n minus 2 plus a square minus I holds for all n greater or equal to 3. So this was the first part of the question. We also have another part in this question, which is finding out a to the power 50. So as you can see here, if I substitute n as 50, what would be the expression a to the power 48? Then a square minus of I. So one thing is not known to us, which is a to the power 48. So again, if I place 48 in place of this n, you will get 46 here, because n minus 2 means 48 minus 2 would be 46. So in that way, if you continue this process, how long you can continue is unless and until you are getting a square here, because in each step this power will be lesser by 2. So in that way, if we continue this process, the value, rather the power of the first term would be a square, the least term would be a square. So do not forget this, a to the power 50, so I will write it once again, a to the power 48 plus a square minus of I. So in that way it would, we have to continue till a square, unless and until we are getting a square, because after that we are unable to do anything. So a square minus I. So the same approach we have to do with this equation. A to the power n, it is a to the power n minus 2 plus a square minus of I. We already have this expression. So in the next step, if I substitute a to the power n minus 2, that would be a to the power n minus 4. Also you will get a square minus of I, the value of a to the power n minus 2. Also you had another a square minus I. So this can be expressed as a to the power n minus 4 plus twice of a square minus I. Simple. See here, again a to the power n minus 4 we are getting. So it can also be expressed as a to the power n minus 6 plus a square minus I. That's the value of a to the power n minus 4 plus twice of a square minus I. So a to the power n minus 6 plus 3 into a square minus I. Now you need to follow this and this, these two equations. Why? Because you see, when it was n minus 4, look at the coefficient, it has become 2. That means it's half of 4. Again you see, when it was 6, it became 6 by 2, that is 3. And the point here, which I already have mentioned you, that we have to continue unless and until we are getting a square. So when will you get a square is, if you write n minus 2. Like in each step, there shall be a difference of 2. So n minus 2 by 2 into a square minus I. So after this, 8 square, look at this, the point which I already have mentioned earlier. Here we are getting a square, n minus 2 by 2 into a square minus n minus 2 by 2 into I. So it is a square plus n by 2 minus 1 into a square minus n minus 2 by 2 into I. So a square after the multiplication, this would become n by 2 into a square minus of a square minus n by 2 n minus 2 by 2 into I. So simply you can cancel out this a square and minus a square. So you are left with n by 2 into a square minus n by 2 minus 1 into I. And that's the value of a to the power n. So more or less it's done. Here in the next step we have to substitute n as 50 because we are supposed to find out the value of a to the power 50. So let's just find out a to the power 50 by substituting n as 50. This would be 25a square minus 24i. That's the final expression. And finally you have to get the value of a square. See, a was given as 1 0 0 1 0 1 0 1 0. So this into this. So after multiplication, a square would be 1 0 0 1 1 0 1 So this is the value of a square which I am going to substitute here. So 25 0 0 25 25 0 and 25 0 25. This is the value of 25a square minus 24i, that means 24 0 0 0 24 0 and 0 0 24. Let's just take the difference. 1 0 0 25 1 0 25 0. So this is the final answer of a to the power 50. Thank you.